before I had to be, but.
Really? That's the Monday after that. I don't know if you get back to that's fine.
All right, so today I have just a few announcements, reminders. There's no homework this week, but there is a group quiz on Friday. And I'm going to move exam 2. It's going to move ahead. It wasn't on Friday. It's now the Monday after that. So now it's going to be October 28th. Yes? There is. Let's see where I have my little cheat sheet. October 11th. There we go, October 11th. That's, yeah, I think it's the Friday before fall break. Yeah. It'll be okay. Yeah, if anyone went to the biology seminar yesterday and you want that to count for credit, make sure you summarize that. Biology is every Tuesday at 11. The auditorium. Yeah, they're always in the auditorium. So, I don't know what they talk about every single week, but it's something. They talk about something every single week at 11. All right, so today we're going to start chapter 6, which starts a 2-3 chapter sequence on enzymes. So today is just, oh, that's very small, is introduction to enzymes. All right, so enzymes. The question is, what is an enzyme? So, enzymes are biological catalysts. Their job is to accelerate biochemical reactions by physically interacting with reactants and products to provide a more favorable pathway for the transformation of product to a reactant to product or vice versa. So an enzyme cannot make an unfavorable reaction favorable. So it cannot change the sign of delta G. So in this case, delta G is positive, which means unfavorable. It can't do anything about that. It can't make an unfavorable reaction favorable. It can, however, change the transition state energy, which we'll look at here in a little bit. For an example of how useful enzymes are, so in vitro, a peptide bond has a half-life of about 20 years. What does it mean to have a half-life? Good thing to review because the next chapter is all kinetics. So it's how long half of it exists before half of it breaks down, right? Half still stays peptide bond, half breaks down. So it takes about 20 years to break down half the peptide bonds. that's an issue because your peptide bonds need to be constantly forming, breaking, remaking, doing other things, right? So should be B. But with the use of an enzyme, the half-life of that bond becomes seconds, which is good, because if you think about, like a real basic example would be like adrenaline, right? It gets formed, and you don't want that hanging about in your body for 20 years. You would be, like, what's that movie? Speed? No. The guy where he has to keep getting injections of adrenaline? Crank. Like the movie Crank. That wouldn't work very well. You know, it's not a good lifestyle. Nobody wants to live like that for a long time, and so it's good to have your proteins build and be able to break down and then build up again and break down again. So we'll take a look at how enzymes do that, what some of their methods are. So does everyone have this? Oh, wait a second. There's a lot of information on there. We'll start talking about some general properties of enzymes. I'm going to give you 4 general properties of enzymes that would be true for all enzymes. And then we'll spend most of the rest of the day talking about delta G, thermodynamics. Pretty excited. We'll do some reaction energy diagrams like you do in organic. Delta G transition state. It'll be good. Okay. All right, so general properties. 4 general properties. First one is higher reaction rates. So the rates of enzymatically catalyzed reactions are 10 to the 6th up to 10 to the 12th times faster than uncatalyzed. Then rates of enzymatically catalyzed reactions are 10 to 1,000 times faster than chemically catalyzed. So let's talk about what does it mean to be chemically catalyzed versus enzymatically catalyzed. So here in my section called milder reaction conditions, let's think about we'll do chemically catalyzed reactions first. So let's say you are in the chemistry lab and you want your reaction to go faster. What are some options of things you can do to speed up your reaction in the lab? Heat it up. We could add heat. Change the pH. I have a third one. I'm sure there's more than that, but
Add more substrate.
you could add more substrate. Stir it. When you're using the rotovap, what is the thing you are doing to make it boil faster? You're adjusting the pressure, right? You're putting it really under a vacuum. So we'll just say change pressure. Okay, so of those 5 options, which of those do you want to do to your body to make your body reactions go faster? We could warm you up. We could stir you around. I guess keep spinning you till you vomit. That may be an option. As we learned from our Bohr cycle, we don't really want to mess with your pH because you'll stop breathing. That's not so good. We could put you in the vacuum, or we could send you to outer space. That is an option. Something would happen to you if I sent you out to outer space. Probably not positive. And then add substrate. Potentially, right? I could feed you. That would be adding substrate, and you might end up happier overall. For our enzymes, I didn't leave myself enough space. What pH do just about all the reactions in your body take place at? Ish. Neutral, 7. So that's good. So all the reactions are at pH about 7. So all the enzymes are able to do that. We don't have to do anything funky with your pH. What temperature does your body typically exist at? 98.6 Fahrenheit, right? Which is good, because just about all those enzymes work at around between 90 and 100 degrees Fahrenheit. Somewhere between 90 and 100, we'll say 90 and 100. Do enzymes require much stirring? Not really. Luckily, there's enough motion in your body to help everything find itself. Do I have to change the pressure for your, what pressure do you currently exist at? Atmospheric. So it's pretty handy that all these are pretty mild conditions. pH 7, mild heat, right? 100 degrees Fahrenheit isn't really all that much in Celsius. All reactions are at 1 atmosphere. So that is good. The enzymes can do all those things without going to extremes, which you sometimes have to do to get your chemical reaction to go. All right, greater reaction specificity. So enzymes are very specific to their substrate, right? They typically only react with 1, maybe 2 things. What happens over here in your chemical catalyzed reaction if I add heat? Does just your product get made, or do other things happen? Other things happen, right? You're adding heat to the whole system. So the likelihood of you making stuff that you don't want increases also. That's why you can't just like turn on full blast in the chemistry lab all the time, because you want only some things to be made. So because there's greater reaction specificity, it's rare to have side products, which means it goes to 100% yield, like your percent yield should, in theory, be 100% every time you're using an enzyme. You don't get what you got in the organic lab, which I'm sure was always 100%, possibly 60%. Not often, right? Because you guys seem pretty stellar. So, enzymes, do it right every single time. Then the last general property for enzymes is that they have a capacity for regulation, which when we get to glycolysis and the citric acid cycle will be the majority of what we've been talking about, how they are regulated. So the catalytic activity of enzymes varies in response to the concentration of not just the substrate, but also inhibitors and enzyme modification. So obviously, right, if you're thinking about the shot liase, if you add more substrate, it should make more product. That is true for enzymes. But also, you could have inhibitors in there, which will spend a good part of this chapter talking about how do inhibitors work and how do you know what kind of inhibition is going on. As well as enzyme modification. Sometimes the enzyme has to be phosphorylated before it can do anything else. And that phosphorylation only happens because the previous step released an ATP, which is then available to come and phosphorylate step number 2, which then releases an ADP, which is then able to come around to the other side and get ATP'd again. And then come back. Anyway, so I know you guys are excited. Citric acid cycle is coming. Very exciting. Lots of different areas we can look at. So those are going to be our 4 general properties for enzymes. So let's talk. How do you go about naming them? And then some more specific information about enzymes. All right, so enzymes are normally named, typically named, by adding the ASE ending to the name of the enzyme's substrate. There is a very systematic method of naming reactions by the International Union of Biochemistry and Molecular Biology. Apparently, those guys unionized and decided to make their own system of naming. Who knew? It's like the IUPAC, right? Those guys got together and came up with the organic naming system. These guys got together and came up with the biochemistry naming system. So, here's my enzyme, alcohol dehydrogenase. Any guesses on what kind of substrate this acts on? Alcohols, what does it do to those alcohols? Dehydrates alcohols, right? It is a fairly straightforward naming system. It's going to dehydrate, and when I say dehydrate, what's going to be my product? Water. Okay, so here is my All right, so here's my alcohol. So in this case, because I'm just drawing it like, draw my enzyme down here. It's going to dehydrate that, which means it's going to release that proton, which then can go on and react to make some water later on. Right, that proton has gone off with that proton, and it's going to go find another. Water is one of my final products. Why did I draw it in equilibrium? Any thoughts? It is. These are mostly going to be equilibrium reactions. What's going to force it to finally make product is going to be this product's going to get used in the next step. And as this disappears, right, it forces it more to products. All right, I think you have a homework question or two about naming. So this is just a table out of your book about what they do. Hydrolysis reactions. Octoreductases do oxidation reductions. Transferases transfer functional group. Hydrolases do hydrolysis reactions. Lysases, right, when you lyse something, it's a group elimination, it breaks it. And and that group elimination forces a double bond to be made. Isomerase does isomerizations. And ligases, that name is not as intuitive, but it's going to be a bond formation with some ATP being made. Okay. Specificity. So what makes enzymes so specific to their substrate? It is these non-covalent forces that are used to bind the substrate into the active site. So what are our 4 non-covalent forces that we know about? Hydrogen bonding, ionic, which your book calls electrostatic. That's the same thing, it means charge-charge interactions. We got 2 more. We're going to do van der Waals because dipole kind of falls into van der Waals. And the last one's not so much a typical force, but we talk about a lot when we talk about folding. Hydrophobic. So in general, a substrate binding site must be geometrically complementary. To the substrate. So what does it mean to be geometrically complementary? As in this picture, right, there are a matching set of, like this is kind of oval and this is kind of square. So the oval goes in the oval spot and the square goes in the square, right? So your square peg round hole dilemma. Your opening has to be the same shape as the thing you're trying to stick into it. And I say in general, because what if you had the reverse, right? Sometimes the circle will fit in the square hole, but the square hole won't hold this, right? There are some flexibilities in those things. So in general, they have to be matching. We'll look at some examples where a smaller substrate can fit into the active site and make some other things, as opposed to what it typically would bind to. Okay, so that's step 1. You gotta have a geometrically complementary site. The amino acids that are in the binding site are specifically arranged to attract the substrate. They are electronically complementary. So we have to have geometric complementary and electronically complementary. So looking back over here at my picture. All right, so we decided that this is the oval, which fits in there, and this is the square, which fits in there. So that would be fine if we just had to worry about geometry. We also have to worry about this electronic complementariness. So here we have a negative charge on my substrate. What kind of charge do you want on your active site then? Positive charge. So here's my positive charge. Here I have a proton, so it's a lone proton, and I'm going to do what kind of binding with a H kind of hanging off something important? Hydrogen bonding. So I need another hydrogen in my active site to pair with that. We have 2 of those. And then I have an amine group over here, which is also looking at hydrogen bond. So there has to be a complementary, probably oxygen, to bind to that. And then here I have my carboxylic oxygen hanging off the end, and it's going to want to hydrogen bond also. So this site has both geometry that fits and electronics that fit. So a substrate that's not able to fit both the electronic and geometry requirements of the active site will not bind productively, so it won't make any product. Questions about any of that? That seems pretty intuitive also. So then let's talk about everybody's favorite, reaction diagrams, activation energy reaction coordinate diagrams. So, one way to understand how an enzyme catalyzes a reaction comes from our understanding of thermodynamics and transition state theory. So, here is my example of transition state theory. Get my colors out. So in this case, I'm looking at 3 hydrogens. I got H2 and a single lone H hanging out by itself. For whatever reason, realizing that that's not possible, but for my example, we'll call it that. Transition state theory says for this example, so for this reaction to occur where they have just swapped partners, right? So I had A, B as a covalent bond. Something happens and now B is linked to C and A is hanging out by itself. So for this reaction to occur, we have to have HC approach the other molecule, the HB molecule. Which means at some point there was a transition state. The transition state was high energy and unstable. So, why must there be a transition state? Chemistry's not magic. And right, I didn't show a step where A and B broke up and they floated around by themselves, and then B found C and A was left over. Right, there had to be a spot where one of these bonds was breaking and one of these bonds was forming. So a transition state for this kind of example would be something like this. where I am breaking the HAB bond and I'm forming a BC bond. Why would I say that that state is unstable? What would happen if that in between was stable? It would stay like that, right? If that was a stable form, then we would see this form. Right? That would, if it was stable, it would make that, when we don't make that. So we can't make a 3-member HHH bond. So, lucky for us, we can plot this kind of information. Who doesn't love a graph? You will by the end of the semester. You either love them or you super, super hate them, but I'm hoping everyone is passionate about graphs. So reactants generally approach each other using the path of lowest energy. That should sound familiar, true, thermodynamically true, good. And we can plot the information on the reaction coordinate. So this here is a reaction coordinate diagram. Did you guys do these in organic? I know for sure you do them in 109. So the reaction coordinate is going to be my x-axis. What's this guy over here on my y-axis? G, which also stands for free energy. So here is the diagram, the reaction that we just did. Here's my A bonded to B. Here's my B bonded to C. Here's my transition state. My transition state that is at high energy and unstable. What is the free energy difference between my starting material or my reactants and my products? Trick question. 0, right? Because if I measure the delta G here and my delta G here, delta G is 0, right? So it's the same. So there's no change in free energy for this example. Why is there no change in free energy for this particular example? Did I make anything different than what I started with? No. My starting reactants look identical to my final products. So there can't be a free energy change because I didn't actually make anything. Right? I did the little shell game and I rearranged the components, but there's still the single golf ball underneath the shells, right? Or solo cups or whatever you guys play your... You guys never play the shell game. But you know what I'm talking about. You put a ball underneath the cups and you, right? I mean, they do it at the baseball games. They put the baseball underneath the helmets on the big screen and you're supposed to follow where the baseball goes. Same thing. So, I don't know why it's called the shell game. I guess at some point they had big shells. That just reminds me how super old I am. And everyone's looking at me like I have no idea what you're talking about. I'm like, I know you know what you're talking about. All right, the last thing to talk about on this diagram is this guy over here, this delta G double dagger. So delta G double dagger is the free energy of activation. And what is that measuring the energy difference of? What are these guys? Starts with an R. Reactants. I already labeled this, transition state. So it's measuring the difference between reactants and transition state. So that is good if I wasn't going to make anything, right? My reactants and products are identical. Doesn't really matter about this free energy of activation, because if it doesn't go over the hill, then that's fine, 'cause I'm making the same thing at the end. So let's look at an example where I am going to make a different product than where I started. So the question I have first on here is, why is this no longer a symmetrical diagram, right? This one is perfectly Gaussian looking, very symmetrical, very pretty. What makes this one less symmetrical? Right? I'm making something different. What is the reaction that I am making in this one? Something, arrow, something. What are my reactants?
A plus B.
A plus B, very good. Just checking to make sure everyone's conscious. Okay, good. What am I making as my final things?
B and Q.
B and Q. So in this case, I am making something different. It is no longer symmetrical because there is a free energy difference between reactants and products. My period got smushed into my T. Great. Okay. Here's my delta G, double dagger again, which is the free energy of activation between my reactants and my transition state. Right. It's important, that's why I'm writing it down twice. So star it on your other pages. What is this guy over here, this delta G of reaction? What is that measuring the difference of? Right, just flat out free energy difference between my reactant spot and my products. What is the sign of this delta G of reaction? Oh, I heard it. Oh, oh. Okay, if I'm here and then I have to go down, it should be negative. Good. I was going to draw a number line here for a second. Like if this is 5 and this is all the way down here at 3, 5 down to 3, right, negative. Good. Okay. If that is negative, is that I guess, spontaneous or non-spontaneous? Excellent. It's overall spontaneous, but it's going to depend on this delta G double dagger. About how much energy I need to get over this, because once I get up here, definitely spontaneous. Oh, bless you. Let's see what else I want to say. Oh. The time spent in this transition state, the X double dagger, is going to be relatively small. I don't even know what prefix is 10 to the negative 13th. Beyond nano. So small. Very small. But this step is going to be the most important to the overall reaction. Does anyone know what RDS stands for in the context of these kinds of problems? This is going to be the rate determining step. So X double dagger in this particular diagram is our rate determining step. You have to be able to make that to get all the way over here. You can't bypass making X double dagger. So that's our rate determining step. So you may be thinking, this is great, I love graphs, but what I really would love to see is an equation. Don't you worry, I got one. Our old friend, the Arrhenius equation from Chem 109. Hey, I know you've missed him. I know you did, you miss him. Arrhenius equation, so reaction rate depends on both the energy and the frequency of collisions. So the Arrhenius equation, which is over here, K equals e to the power of negative delta G double dagger divided by RT. Let's take a tour through all those letters. It's gonna be our rate, reaction rate. I put the approximate in here because I'm missing some of the other information from the Arrhenius equation, but I just want to look at some of the big parts, the K and that guy over there. We just had, okay, this is supposed to be double dagger, but my computer doesn't have that symbol, so it's a plus minus. So in yours, actually make it a double dagger. For whatever reason, my computer doesn't own that symbol. What is R in these kinds of equations? Which kind of gas? Yes, it's the gas constant, and depending on what units you have around it, you're either going to use the 8.314 joules per mole Kelvin or the 0.008. Okay.
Wait, can you tell us the gas constant?
Sure, we're going to use 8.314 joules per mole K. There is the other option of the gas constant, but we don't need it for this equation. So based on the fact that the gas constant is in units of joules per mole K, what should my temperature be measured in? Excellent choice. So, using my Arrhenius equation that says that the reaction rate, which is K, depends on energy, and this RT is telling me about the frequency of collisions. If you are at higher temperatures, do you have more or less energy? Typically. More energy, right? If you have more energy, how likely is it you're going to run into somebody else? More likely. So that's what the Arrhenius equation is really getting at, that if you increase the temperature, you have more energy, you're zooping about, you're more likely to run somebody than you are if you are at a cold temperature. So this is often how we talk about, like, why do you heat water to get things to cook? Because it has more energy and it runs into the molecules and gives them their energy. Okay, good. Oop, no, I lost my place. Where am I at? 6.5. 6.6, there we go. So using this equation, using this equation, we can see that the greater the value of delta G double dagger, which is telling us about the height, the transition state, right? How much energy it takes to get to the transition state. The greater the value of that, the slower the reaction goes. So the reaction rate has to decrease. So let's think about this. We'll do it numerically here in a second. But thinking through this thought process, the greater the value of G, so if I draw two quick sketches of some reaction diagrams, all right, so I have one with a large delta G double dagger and one with a tiny delta G double dagger. So tiny, I kind of ran out of space to make that look pretty. So delta G double dagger, very small. I look at the small delta G double dagger. What is the probability that most of the molecules have enough energy to jump this hump, because it is hump day, jump over this and slide down to the other side? Right, small delta G. Most of them have enough energy to get over the transition state to make it to products. Over here, do you think the same proportion or smaller? Smaller. Less of the molecules have enough energy to get to the top to slide back down to products. So the larger the delta G double dagger, the smaller number of molecules have enough energy to achieve the transition state. And so we can mathematically prove this approximately. So we can prove it approximately. So if you plugged in 20 as your transition state, which would be more like this guy would be a height of 20, where this guy over here would be my 500, approximately, right? This one's smaller than that one. Using the same gas constant and assuming we're all at the same temperature, 273 Kelvin. So the rate constant, the reaction rate, the likelihood I make it all the way to products, for a delta G double dagger of 20 is about 0.99. What's a good value for K? 1. It is 1. So the closer you are to 1, the more likely you are to make it all the way to products. So that's pretty good. And K is really kind of a measurement of the proportion of how many reactants will make it all the way to products. So we can think about this as 99% of the reactants make it to products at a low delta G double dagger. When I increase the delta G double dagger, what is that? It's 10, 20, like 25 times bigger. About. Now only 80% of them have enough energy to make it all the way to products. So that transition state energy has a huge influence on how much we're going to make. Lucky for us, we all have enzymes, and we'll talk about that on Friday, about how enzymes affect delta G double dagger.